Okay, let's get started. So while we are waiting for our friends, so we are going to do a quick review on what we just did on Monday. So review. So what we just did on Monday, we said that we can define definite integrals. And our notation for definite integrals is going to be integrate from a to b fx dx. So the notation here, I just add lower bound and upper bound here, which is a and b here. And in order to compute the definite integral from a to b, so if you use a definition, this is definition, so it's going to be integrate from a to b function f. You have to go by using the Riemann sum. So you're going to compute the limit when n go to infinity of the Riemann sum, summation I from 1 to n, fxi star times xi minus xi minus 1. This is going to be the approach that we do not use it for this class because this approach is so hard to use because you have to compute Riemann sum and then you have to take limit, which is time consuming. So we're gonna avoid using definition. To compute integral from a to b, we have fundamental theorem of calculus. Fundamental theorem of calculus. This is going to be the one that we use to compute our definite integrals because it reduces to the form that it is easy for us to compute. So it's going to be integrate from a to b fx dx. So you can compute this thing by find the antiderivative capital F first, and then you evaluate antiderivative at b minus antiderivative at a, where f is an antiderivative of f. So this is the core idea that we just did on Monday. So today we are going to practice how to use the fundamental theorem of calculus part 2. The theory is not that hard. This is going to be the form that we use all the time, but the hardest part for integration is the technique. So for each question, you're gonna learn different techniques that we approach definite integrals. So let's start by looking at example 71. So example 71 here, I want you to compute integral from 0 to 2 absolute value of x squared minus 3x plus 2. So every time when you see absolute value, I would recommend you to get rid of the absolute value first. That would be a good idea. That would be a good start all the time. So today we are going to start from x squared minus 3x plus 2. Well, we will try to simplify this thing first. So this is going to be, how do I simplify this thing? How do I get rid of the absolute value? So the idea is the same. So we need to consider the thing inside the absolute value, right? If the thing inside the absolute value is positive, so it's gonna come back to positive thing. Well, if the thing inside absolute value is negative, so it's gonna be negative that thing, where that thing less than 0. So we learn this thing when we learn limit of absolute value. So the same idea. So we are going to say that this is x squared minus 3x plus 2 if the thing inside absolute value is positive, right? Well, it's going to be negative x squared minus 3x plus 2 in parentheses if your x squared minus 3x plus 2 less than 0. Well, that means it's going to be x squared minus 3x plus 2 if, well, what does it mean by x squared minus 3x plus 2 greater than 0? So you can see that you can factor this thing. So I'm going to factor that to be x minus 1 and x minus 2 greater than 0, right? So another function is going to be minus x squared plus 3x minus 2. This is when x minus 1 times x minus 2 less than 0. Well, if you solve that inequality, this is going to be, so I am lazy to write the whole thing, so I'm going to copy that. Gonna paste that. All right, so I'm gonna simplify x minus 1 times x minus 2 greater than 0 to something else. So when x minus 1 times x minus 2 greater than 0, what does it mean? So, well, if you remember from the previous algebra, if you have that inequality, so it means your solution for equality, this is going to be 1 and 2, right? And then you want the interval that x minus 1 times x minus 2 greater than or equal to 0, you can start from this plus, this is minus, this is plus. So that means your answer for the inequality when x minus 1 times x minus 2 greater than or equal to 0 is going to be the one that I highlight in light blue. So if it falls in between 1 and 2, it is going to be the case that I highlight in green. So that means if your x less than or equal to 1 or x greater than or equal to 2, it's going to be that function. And also when x is in between 1 and 2, this is going to be the second function. So now once you get rid of your absolute value, now you can integrate. So how do you integrate this thing? So you need to integrate from 0 to 2. Well, your 0 to 2 is here. 0 to 2. Right? This is the interval that you need to integrate with respect to. So it's mean from 0 to 1, you're going to use the function x squared minus 3x plus 2. And when x is between 1 and 2, you're going to use negative x squared plus 3x minus 2. All right, so let's do that. So here, you're going to get integrate from 0 to 2 of x squared minus 3x plus 2 dx. So I'm going to split into two pieces. So that's it's going to be integrate from 0 to 1. X squared minus 3x plus 2 dx. And then plus integrate from 1 to 2. Negative x squared plus 3x minus 2 dx. All right. This is because from 0 to 1, I use the first function. So from 1 to 2, I use the second function. Right? And then after that, I just need to use the basic integration now. So I want to integrate x squared minus 3x plus 2. So I'm going to get x cubed over 3 minus 3x squared over 2, right? Plus 2x. And then I evaluate this at x equal to 1, at x equal to 0, and then minus negative, plus negative x cubed over 3 plus 3x squared over 2, and then minus 2x. And then I evaluate at x equal to 2 minus x equal to 1. Well, you can plug in this number, so you're going to get 1/3 minus 3 over 2 plus 2. And then once you plug in 0, everything going to be 0. And then you plus negative 2 cubed over 3, and then plus 3 times 4 over 2 minus 2 times 2. That is going to be the first term when you evaluate at x equal to 2, and then you minus when x equal to 1. Well, the remaining work, this is going to be just calculation. So you can compute this thing by your own, and well, it's gonna cancel out perfectly and you get a answer 1. Well, you can try. So the number gonna cancel out perfectly and then you get 1. Make sense? Well, this is how we deal with absolute value. So remember that when we deal with absolute value, the standard trick is you're trying to get rid of your absolute value first. Once you get rid of your absolute value, well, you can split your integral into 2 pieces or more than 2 pieces. It depends on what piecewise function that you get. And then after that, you integrate with respect to that x value. All right. Any question on example 71? Well, before we go ahead to another example, let me tell you that today we are going to go over medium to hard examples. It's going to be a tough lecture today because every problem I show you today, they are not easy. They are medium to hard one. So this is supposed to be the question for top up student into grade A, grade B plus, grade B, grade C plus, or something like that. So this is going to be the one that is challenging on the exam. All right, example 71, that is done. All right, if you don't have any questions, well, you can leave your question anytime in the chat, but we're gonna move to example 72. All right, so let's look at another question. This one is the trick again with sine square. I told you before that when you see sine square, you have no choice. The only choice that you have for sine square and cosine square is using identity. That is the only choice you have, because if you're trying to use u substitution, if you pick u equal to sine 2 theta, and then you compute the u equal to this side, you get cosine, and then you use the chain rule, you get 2 here, and then you're trying to use a u substitution or whatever, you're gonna get stuck because it will not cancel out perfectly. So the only the only solution that you're gonna deal with sine square is using identity. So remember that sine square of the angle A, this is going to be 1 minus cosine 2 of angle A over 2. This is the formula for sine square. So if I want sine square of 2 theta, so I have to replace A by 2 theta, and this is going to be 1 minus cosine 4 times theta over 2, right? I'm trying to go slow by, I'm saying that I replace A by 2 theta, so you get 2A equal to 4 theta. And then now, once you use this trick, it's going to be easy because we are going to integrate sine square of 2 theta, right? I'm going to switch it to 1 minus cosine 4 theta over 2 d theta, theta from negative pi over 4 to pi over 4. All right, and because you see constant now, so you can pull out your constant 1/2. I love to pull out constant first all the time because it's gonna make our term in the integrand a lot easier. And then now I split my integrand into 2 pieces. So integrate from negative pi over 4 to pi over 4, 1 d theta, and then plus integrate cosine 4 theta from negative pi over 4 to pi over 4 d theta. All right, next I'm going to integrate 1 d theta, so I get theta. And then I evaluate at theta equal to pi over 4. Theta equal to negative pi over 4. All right. Well, let's look at the second term here. How do I deal with integrate cosine 4 theta d theta? So I'm going to do it quick. So let's see if you can follow me if I do this. So I'm going to integrate cosine 4 theta. So I'm going to switch d theta to d4 theta. Well, this is similar to I pick u equal to 4 theta, and then I divide it by 4. Well, this is the way we pick your new variable quickly. So you don't have to set u equal to 4 theta all the time because it's going to be too slow. So once you feel like you are more comfortable with your substitution, you can just do this. And then now I'm going to say, hey, because I change now from theta to d4 theta, I'm going to say, well, keep in mind that what I have to plug in at the end, I have to plug in theta equal to negative pi over 4 equal to theta equal to pi over 4. I just wrote theta equal because I want to keep in mind that that number is the number for theta. So when you plug in number, so you can plug in correctly. So after that, I plug in this, so I get pi over 4 minus pi over 4. Right, that's the first one. And then plus, so now I have a quarter time integrate cosine 4 theta, d4 theta, so you get sine 4 theta. And then you evaluate at theta equal to pi over 4 minus theta equal to negative pi over 4. Right, and then that you're gonna get 1/2 times pi over 4 times 2. This is pi over 2. And then plus a quarter, and then that number is going to be sine pi minus sine negative pi. All right, does it make sense? Oh, it's still pretty simple, right? Sine pi is equal to 0, and sine negative pi is also equal to 0. So that's mean your answer gonna be just pi over 4, right? Because it's gonna be, you're gonna get 1/2 times pi over 2 plus 0, because your sine theta is 0 and your sine minus your sine pi is 0 and your sine negative pi is also 0. So this term gonna end up with 0. Well, that means your answer is clean enough. So you're gonna answer pi over 4. Sounds good? So this is example 72. Well, this example is good because after midterm, as I told you that we're gonna learn how to integrate trigonometric function. So you're gonna use this technique again and again after midterm. All right, so next, well, I told you each example today it's gonna be tough. So example 73, so let's compute integral from 4 to 9. Square root x minus 1 square over 2 square root x dx. So what should I do for this one? So you can see that what I have square root x minus 1 and then square. Some of you are gonna say that, hey Ajahn, when I see this thing, don't copy yet. So you can think that you're gonna expand square root x minus 1 square equals square root x square, and then minus 2 times that, right? And then minus 1 square. This is one way to do it. You can expand square root x minus 1 square, so you get that, which is going to be x minus 2 square root x minus 1. Oh, this is going to be plus 1, sorry. That plus 1. You can do this one if you want. And then once you integrate that, hopefully you end up with something that you can integrate. So I'm going to integrate that, right? And then I have to integrate that. And then I have to integrate that. Well, if you want, you can do that. This is solution number one. However, I'm not going to do this way because I do not like to expand it. I don't like to expand square root x minus 1. So if you can do this, yeah, go for it. Well, sometimes expanding is harder because you're going to end up with the term you do not know how to integrate, right? But this time, it will work because you're going to cancel something and then you're going to end up with x to the some power anyway, so you can integrate. However, what I'm going to do here is we're going to use u substitution. So I'm going to pick u equal to square root x minus 1. And then you will see what happened. If I pick u equal to square root x minus 1, so I'm going to get du equal to, I differentiate square root x. So I get 1 over 2 square root x. Differentiate 1, I get 0. So for those of you who cannot follow me, so x square root x is x to the 1/2. If you take the derivative of square root x, that means you take the derivative of x to the 1/2. Oh, that thing is going to be 1/2 x to the negative 1/2. And that is 1 over 2 square root x. Because we use this thing again and again all the time, so I just memorize it. Because when I see square root x, well, I get the answer automatically. Yeah, so my differentiable, my derivative of square root x, this is going to be 1 over 2 square root x. Well, if you do problem again and again, you're gonna feel like, hey, this should be a formula because we use it all the time. So anyway, so this question, I differentiate square root x, so I get that. And then you can see that, well, if you write the x in terms of du, you're going to get the x equal to 2 square root x du. Easy, right? So that means your given integral, this is going to be integral from of u square over 2 square root x. And then the x here going to switch to 2 square root x du. Which means, oh my God, Ajahn, 2 square root x cancel. Well, what you have left, you just have integral from u squared du, right? And then now you can integrate u squared du. Whoa, that will leave us a nice answer. But what is our lower bound and upper bound here? So let's take a step back and look at 4 and 9 here. So when x equal to 4, what happened with u? So when x equal to 4, so you're going to have u equal to square root x minus 1, which is square root 4 minus 1. This is 2 minus 1. This is 1. So that means when x equal to 4, you get u equal to 1. So your lower bound of integration going to switch to 1 here. Make sense? When x equal to 9, your u going to be square root x minus 1. So that's u going to be square root 9 minus 1. This is 3 minus 1. This is 2. All right. So that means this is 1 to 2. And then when you integrate u squared, you're going to get u cubed over 3. Right? And then you evaluate at u equal to 2 and u equal to 1. Your answer is going to be 8 over 3 minus 1 over 3, which is 7 over 3. This is how to write the solution. And then if you show your work like this, full credit. Some student going to say that, Ajahn, can I do this? This is another way to do this problem. So some of you are going to say, Ajahn Krab, if I do integrate from 4 to 9 square root x minus 1 square over 2 square root x dx, if I integrate this and then I say, hey, I change this thing to u, and I'm lazy to change the lower bound from x to u, can I leave this thing to be 1 to 2? Sorry, can I leave this thing to be 4 to 9? And then you're gonna say that, well, after I cancel that, so I'm gonna get u square from du from 4 to 9. So you can see that if you leave 4 to 9 here, you could make a mistake because you have to keep in mind that 4 to 9, this is x. So I would recommend that if you do not want to switch from x to u immediately, say that this is x to 9. Just write the whole thing. So this is gonna keep you on track that the value here is x, not u. This is acceptable on the exam too. When you say integrate from 4 to 9, you have to specify that this is your x. If you leave it 4 to 9 without saying anything, you lose your point because we don't know that this 4 to 9, this is u or x. I mean, it's confusing, but if you didn't say anything, that 4 to 9 number, that thing is going to be u. Well, the number here gonna base on the variable at the end here. So if you already switch to du, it means your lower bound and upper bound, those are numbers with respect to u, unless you specify this is x. And then some of you are gonna say, hey, I can integrate that to u cube over 3, Ajahn. And then I'm gonna get that, and then you have to write at x equal to 9 and x equal to 4. And then you can plug in u back now. So you're gonna get square root x minus 1 cube over 3. And then you plug in x equal to 9, x equal to 4. Doesn't matter, you can do this thing too. So you get 7 over 3. You can do two ways, the way that I wrote in blue or the way that I wrote in green. Well, you should get different, you should get the same answer because they are the same way. But some of you are gonna feel like I am more comfortable to switch everything to you first. Some of you are gonna say that I'm more comfortable to just integrate first and then plug in later. Depends on you. It's your choice. Does it make sense? For me, sometimes I like to plug in at the end. Sometimes I just love to change it to you immediately. It depends on the problem. But keep in mind that you have two choices. You can do whatever you want. Does it make sense? All right. Or be careful when you write the solution here, because if you skip steps, you will not get credit on the exam. So on the exam, we are so specific about what you wrote. If you are not sure that, hey, I'm not sure, Ajahn, that my solution is too short. I'm not sure this is acceptable. Just send me an email. So I will check it for you that this is not acceptable or this is acceptable when you show your work for the homework or exam. But usually if you show your work as I did in class, usually no problem, because this is have so many details in your work. All right, so we're gonna keep doing examples for today. So we have two more examples, right? Which is the hard one for this chapter. So let's do example 74 and 75. So before that, Chuin have a question. Excuse me. Chuin said that, can I use u equal to square root x? And that u square gonna be x. And then 2 du is equal to dx. Okay, before we move on, let's answer Chuin's question. So Chuin asks that, well, if we have, well, think of that, people. So when we have, well, I forgot the question. So let me open the question first. Let's see. Okay, we have integrate from square root x minus 1 square over to square root x dx. So our friend said that, can we pick u equal to square root x? We could try. So we're gonna pick u equal to square root x, and then what happened is I'm gonna get du equal to 1 over 2 square root x, right? Over the x here. And then if you pick just u to be square root x, So your integrand gonna switch to integrate from u minus 1 square here, and then I have the x equal to 2 square root x du, right? And then over 2 square root x here. Seems like everything worked perfectly because I can cancel that, right? And then, whoa, I just keep this thing to be x first. I'm lazy to switch now. X equal to 4, x equal to 9, right? So, and then you integrate that u minus 1 square du, x 4 to 9. Good. So answer to Shuin question, yes, you can. Right? Yes, you can pick u equal to square root x. This is correct too. Because at the end, when you integrate, you can integrate this thing easily. Right? You're going to get u squared minus 2u plus 1. And of course, you can integrate this thing easily. The different thing is because you pick u equal to square root x. So your upper bound and lower bound here are going to be 2 to 3. Right? Because u is just square root x. Well, why did I say that Turing question is so good? Because this shows us that for one question, you can pick different u, but you're gonna get the same answer. Does it make sense? So we can pick different u, me, you, and your friend, and whoever. We can pick different u, or we can go by different method. But at the end, we should get the same answer. All right. Sounds good. All right. So let's move to example 74. All right. So this is going to be I would say this is going to be almost the hard one for the exam, I guess, if it show up. So I have integrate x squared, x to the 5th power over square root x squared plus 1. Still simple, but anyway. All right, so what is your u here? Type in the chat, please. What is going to be your u for this question? Is it obvious? So what is your guess for our substitution here? What is your guess for you? All right. In the chat, everyone, if you are listening to me now in the chat, type in the chat what are you going to pick for the variable u. I will leave you about 30 seconds to think. I think Nachanon, he just had a typo, right? X squared minus 1. All right, Naprata, have a good answer. Yeah, x squared plus 1. All right. Well, for those of you who have more experience, you're going to see it easily that, well, x squared minus 1, this is under square root sign. Well, why don't we try to do a substitution by let u equal to x squared plus 1? Well, my trick is that you should not be afraid to pick u. Well, sometimes you're going to pick u wrong on the first time. Fine. You can fix it later, but don't leave the answer blank when it hit to the exam or homework, something like that. Write everything you know or you can do. Because if you leave it blank, that means you give up, you get 0 immediately. But if you write something, maybe it's going to hit some partial credit. So here I'm going to let u equal to x squared plus 1. I don't know it's going to work or not, but I let u to be x squared plus 1 work first. So for sure, if I let u equal to x squared plus 1, so I have du by dx equal to 2x. Well, and then that means I have dx equal to du over 2x. I'm going to try to switch anything to the form I want. So this is going to be integral from x to the 5th power over square root u, right? I pick u here. And then I change the x to du over 2x. Well, I'm not going to be worried about my lower bound, upper bound now. So I'm going to look at my integrand first, and I hope that I can integrate that. So if you look at my integrand now, so you can see that x going to cancel one time. So I'm going to get integrate from x going to cancel one time here and here, right? So you're gonna get x to the fourth power on the top, and then you have over square root u. I pull out 1/2, so I have du here. Oops, sorry. Oops. Oops. Okay. All right. So this is what you have now. Can you integrate x to the fourth power over square root u? Well, the thing is that we need to adjust something on x to the fourth power. Can we? So you can look at what you just did on the substitution here. U equal to x squared plus 1. Could be. So you can do u minus 1 equal to x squared, right? Because you subtract 1 on both sides. And then that means if you square it, u minus 1 squared going to be x to the fourth power. So let's try it. So this is going to be 1/2 integrate. So I'm going to replace my x to the fourth power with u minus 1 squared over square root u. Sounds good. This is easy to integrate. So I'm gonna say that after that I expand u minus 1 squared. So I'm gonna get u squared minus 2u plus 1 over square root u, right? Du. That is good because I'm gonna get 1/2 integrate u squared over square root u is u to the 1/2, right? Minus 2 times u to the 1/2 plus 1 times u to the 1/2. It seems like this is it looks so hard, but actually this is just only polynomial now. So you can have 1/2, and then that is integrate u to the 2 minus 1/2. This is 3 over 2. So I simplify first, and that is u to the 2 u to the 1/2, and then plus u to the negative 1/2 du, right? And then after that, I can integrate now. So that is going to be 1/2 times u to the 5 over 2 over 5 over 2. So when I integrate, I add 1, right, on the power. So well, minus 2 times u to the 3 over 2 over 3 over 2, and then plus u to the 1 over 2 over 1 over 2. And then I have to derivate at u equal to something. Well, it seems like we can integrate it, but what are we missing now is the value of u. So let's think. So if I pick u equal to x squared plus 1, so when x equal to 0, u equal to 0 squared plus 1, right? Because u equal to x squared plus 1. So this is 1. And when x equal to square root 3, this is going to be u equal to square root 3 squared plus 1. This is tick tock, square root 3 square is 3, 3 plus 1 is 4. So I'm gonna change everything to 1 to 4, 1 to 4, 1 to 4. This is what I usually do. So you have to say that this is 1 to 4 because you already switch your variable to u. If you keep saying 0 to square root 3 all the way down, you lose your point because you already switched to u. You have to make sure that your lower bound and upper bound match with your variable now. So I'm gonna say 1 to 4. Does it make sense? If you feel like, hey, Ajahn, I do not want to switch immediately. So as I told you, you can just keep saying 0 to square root 3, but you have to say that this is your x. That is acceptable. But once you pick your u and you change your variable to du, well, I would recommend you to switch your u. If it's trying to leave about blank calculation. Well, I will answer Batman question and Peterson question in a minute, but let me finish this thing. So after that I plug in number 4 and number 1, and then I compute it. So I will leave this thing for you. This is just only calculation. So the number is going to be tedious. So I get 38 over 15. This is my answer. So you can check it at home, but this is not that hard now because you plug in number 4 and number 1 and then subtract each other. So that will be your answer for this question. Well, let me read your question in the chat. Peter Sud first, he asked me, is it fine to leave upper bound and lower bound blank during the calculation in case that I have to show my work? And Batman said, can we use the area of the circle of the graph to solve this? So that's a different question. So Peter Sud first, so answer that you can. So some of you are going to say that, well, if you do not want to mess up with your lower bound and upper bound, what you can do is, I will show you here. So usually some students have a hard time to put the lower and upper bound immediately. So let's say you have, I cannot remember the question. Whoa, 1 second. X to the 5th power, okay. Well, let's say you want to integrate x to the 5th power square root x squared plus 1 dx, x from 0 to square root 3. Well, if you feel like you want to integrate without the upper bound and lower bound first, you can try to integrate here and you leave it as the indefinite integral first. You're going to say, Ajahn, we are going to integrate that. And well, once you get your answer, so you're going to leave something in terms of capital F, right? Plus C. You show this thing first, fine. Well, on the way you show this thing, I mean, on the way you show your work, you don't have to put the upper bound and lower bound here because this is indefinite integrals. But when you sum up for to submit your work, you're gonna say, okay, I already know this thing, so now I plug in upper bound and lower bound. So fine. And then you're gonna answer this is f of square root 3 minus f of 0. Good. C gonna cancel out. Fine. This is similar thing to when you integrate, you get f, right? And then you evaluate at x equal to square root 3 and x equal to 0. Fine. So sometimes it is easy to integrate first and then you plug in the number at the end. So when we learn integration by parts after midterm, because your solution that you're gonna do it on the way is so messy. So sometimes I love to integrate it first as well and then plug in the number at the end. Depends on your choice. So I hope that answered Pierce's questions. Next, Batman said, can we use the area of the circle graph to solve this? Can we? So when you see x squared minus 1 here, well, if you feel like you can draw the graph of x squared or x to the 5th power over square root x squared minus plus 1, well, yeah, I mean, if you know the graph of x to the 5th power over square root x squared plus 1, and then you can draw the graph, and then you can look at the shape of the graph, and then you integrate from 0 to square root 3 by computing the area above the x-axis of that function. I mean, of that shape. However, for this question, for now, I don't see the way to use the geometric area at all, because this is not a circle, right? Y equal to x to the 5th power over square root x squared plus 1. This is not a circle, so we cannot. Well, at this point, we cannot. But I mean, maybe you can, but for me, I'm not expert in geometry, so I don't know how to do that by using the half of the circle or something. All right. So, well, I still cannot think of the way we can do it by using the circle. Anyway, I'm gonna skip that solution because I don't know how to do it without using just the the geometric interpretation of integration. So I think this is the easiest way to do this question number 74. So you have to go it by using U substitution. All right, so thank you for those questions. I appreciate that, Batman and Piersut, that motivate us to learn. So next, we are going to look at the last example for this chapter, example 75. Whoa, this is going to be the hard one. on the exam if it show up. So this is similar to the hard one, the one that we're gonna cut off A and B plus student or something like that. So let's do this question, evaluate integral from 0 to 1 square root x minus x square root x dx. Well, I just told you that the hard thing about integration is it is not trivial what you should do when you see the question for the first time. When you see the question for the first time like this, you have no idea how to deal with it unless you just get started and do a sketch of it. If you just take a look at the problem and you don't do anything, you don't pick your U, you don't try to do it, you're gonna leave it blank anyway, right, on the exam, because you haven't started anything. So I'm gonna try to start it here. So what is your guess for your U here? Type in the chat, please. So what is going to be your guess for U here, for your variable U here? If it is wrong, that's fine, we're gonna fix it. But what is your guess for variable U here? So let me guess first. So if I don't know nothing, I do not know anything, so I'm gonna start by picking that. So if I do not know anything, so I'm gonna pick U to be everything under square root sign. So I pick that. Well, if I pick anything under square root sign, so what I have du by dx is gonna be 1 minus, whoa, this is x minus x to the 3 over 2. So this is 3 over 2 x to the 1/2. This is 1 minus 3 over 2 square root x. That is not going to be better, I guess. Well, if you're trying that, so you're going to get integrate square root u. Well, the integrand looks simple now, but by doing that, you get dx over 1 minus 3 over 2 square root x. Because you have to switch the x. Oops, sorry, this is du. 1 second. Oops, this is du. Well, even you can make the integrand look nicer by this, you just change it to square root u. But what happened to your dx? You switch it to du over that, right? Terrible, right? Because this looks good, but you just make more problem here. 1 minus 3 over 2 square root x. And I see you have no choice. I mean, you have no way to switch 1 minus 3 over 2 square root x back to u. This is not a good way. So give up. This is not a good choice. So what about u equal to square root x? Well, let's try just a simple one here. So you can say, oh, this is du over dx. This is 1 over 2 square root x. And then that is going to be 1 over x minus x times u. Right? Because I pick my square root x to be my u. And then my dx is going to be 2 square root x du. Better? So this is going to be integrate square root x times 1 minus u, right? Because you can pull out x. And then that is 2, and then square root x. This is u again, and then du. And then that is 2 times integrate square root x, square root 1 minus u times u du, right? I can switch my square root x to u. And then that is to integrate u square, square root 1 minus u du. Is that better? I still don't like that, right? Because if you pick your u to be square root x, at some point you're gonna get this, and you have to ask yourself, can you integrate that? Well, for me, I feel like this is hard because I have square root 1 minus u anyway. When I try to expand u square here into that, well, it seems still messy to me because I don't know how to deal with that term. So maybe this is not a good choice. Well, this is going to be your problem when you do the exam, because you don't know what is the correct u that you're gonna pick. So you may have to try 2 or 3 times until you hit the correct answer. So for this question, I think u equal to square root x is not a good choice. So Peter should say in the chat, that he wanna do 1 minus square root x. Let's do that and see if it gets better if we do u equal to 1 minus square root x. So what he just suggests us, he said that why don't we just pull out x first, right? And then he said that split this thing to, okay, no, not yet. So he pull out x. So he see 1 minus square root x here. He want to do that. So we're going to do du equal to both 0 here. And then minus differentiate square root x. So you get 1 over 2 square root x. Well, that means the x going to be, well, negative 2 square root x du. I'm sorry. Did I do something wrong? Oh no, I'm good. So that, and then after that, I replace this thing. So I'm gonna get root x. Well, 1 minus square root x, I say this is my u. And then my dx gonna be negative 2 square root x du. All right. We say this is going to be my square root x square root u. And then, well, I pull out my negative 2. Then integrate that and then square root x du. So because I have square root x 2 times, so I can group it up. So it's going to be negative 2 integrate x square root u du. Better or not? So you can see that now we need to get rid of x, which we can, right? If you look at the substitution that we just did, so you can see that we have u equal to 1 minus square root x. Well, that means square root x gonna be u, square root x gonna be 1 minus u. And that means x squared gonna be, not just x, because I square it, it's gonna be 1 minus u squared. All right, so I'm gonna replace that. It's gonna be negative 2 integrate 1 minus u squared square root u du. I like it because after I expand that, so I'm gonna get 1 minus 2u plus u squared and then square root u du. And then if I expand everything, so I'm gonna get u to the 1/2, right? Because square root u is u to the 1/2, right? So if I expand that, I'm gonna get u to the 1/2 minus 2 times u to the 3 over 2 plus u times 5 raised to the 5 over 2, right? And then after that you integrate that, so you're gonna get u to the 3 over 2 over 3 over 2 and then minus u to the 5 over 2 over 5 over 2 and then plus u to the 7 over 2 over 7 over 2 and then you evaluate at something. Well, because this is going to be my correct substitution, I'm gonna say when x equal to 0, u equal to what? U equal to 1. And then when x equal to 1, u equal to 0. So that means the upper bound and lower bound of the integration gonna swap. So here gonna get u from 1 to 0. You still with me? And then that's 1 to 0. And then once you plug in everything, you're gonna get the answer. So negative 2 times. I love 0 so much because when I plug in 0, everything is gonna be 0. And that is 2/3, right? and then minus 4 over 5, and then plus 2 over 7. And then your answer gonna be negative 32 over 105. Well, just simplify it, which I already did ahead of time. So that is going to be your answer for this question. You see that this question is hard because we don't know what you were gonna pick. Thank you, Pirasud, that he answered the correct answer for us. However, you can see that when you read the solution, it seems easy because you can follow everything easily. However, the hardest part for calculus is when you think, and it's going to be your experience what variable you're going to pick here. Well, if you know how to get started, well, the rest is going to be easy. All right. So that is at the end of chapter 3. Any questions so far? It's 4 p.m. now. Any questions so far for this chapter? All right. So if not, so I am going to get an introduction to chapter 4. So we're gonna start chapter 4 like next week. Should the answer be positive? Well, maybe I'm wrong. Oh, I forgot the sign here. Thank you for noticing that to me. So when you evaluate that, so I did it too fast, sorry guys. So I did it too fast here. When you see u equal to 0, minus u equal to 1, right? You have to plug in 0 first, and then minus you evaluate at 1. So actually, this is going to be negative. 1 second. Thank you, thank you. So that's going to be negative 2 times 0 first, right? When I plug in u equal to 0. So when I plug in u equal to 0, so I get 0 here. And then I plug in u equal to 1. So I get that. So the answer is going to be f, capital F of 0 minus capital F of 1. Thank you, everyone. Thank you, Supasin, Supavit, and Ganpot. So I forgot that. I did it too fast. So good catch. Yeah, so this is plus 32 over 105. Good. Sounds good. All right. Anything else? You agree with me, everyone? All right. I know the content for today is so tough. Well, if you feel like you have a hard time to follow it, that's pretty normal for the first time calculus student. When I was a kid like you, I feel like, yeah, this is hard. Yeah, this is going to be the one that integration is going to be the one that you have to practice a lot until you absorb the technique. But differentiation is the easy one because once you memorize the formula, so you can do whatever the problem is. You have so many formula for differentiation. It's going to be a lot easier. So if you're done with this example, so you can download the lecture note for chapter 4. We're gonna talk a little bit for 10 more minutes, and then we're gonna let you go for today. Sounds good? All right, so if you download the lecture 4 note, it's going to be this one. All right, so this is going to be the lecture 4, lecture for chapter 4, which is the transcendental function. So transcendental function means the function that does not satisfy the polynomial equation. Well, in other words, this is going to be the function that cannot be expressed in terms of a finite sequence of algebraic function of addition, subtraction, multiplication, division, or something like that. Well, by this I mean on this chapter, which is going to be the last one for midterm, we're going to learn the function that is not polynomial. And those functions, we cannot express it as a finite sequence of polynomial. For example, we're going to learn what is logarithm function. So what is exponential function? What is inverse trigonometric function or and trigonometric function as well. So we're going to learn 4 specific functions. So this is the intro. So we're going to learn 4 specific functions. The first one that we're going to learn is natural logarithm. Number 2 that we're going to learn is going to be exponential function. The third one that we're going to learn is trigonometric function. So this one you already learned a little bit. You know how to differentiate already. And you know how to integrate a little bit already. We're going to add more formula for trigonometric functions. And number 4 is inverse trigonometric function. We're going to learn this 4 function on this chapter. And we're going to look at more problem when we do derivatives and integration when we face these 4 types of functions. So today we have about 10 minutes left. So we are going to look at natural log first. So natural logarithm is the function that is defined to be integral from 1 to x 1 over t dt. This is a formal definition of logarithm. I'm pretty sure you have not seen this thing before in your life. This is your first time that you see the formal definition of logarithm, natural logarithm. So the notation for natural logarithm is logarithm of x. Wrote it as ln. L stands for logarithm, n stands for natural. So natural logarithm of x. I am going to call this thing log x, not ln x. We are not going to say this is ln x. We're going to call log x. Well, this is read as log x. Does it make sense? Well, I don't know how you learn in high school, but this is read at, I mean, everyone in this world, maybe except Thai people, we're going to read this notation as log x. And this is a formal definition for log x, and we don't have to memorize it. We do not need to memorize it. So why do I mention natural logarithm? The reason why I mention natural logarithm here, you can look at the definition of natural logarithm here. If I differentiate log x, what happened? I integrate from 1 to x 1 over t dt. And by the fundamental theory of calculus, this is going to be just 1 over x, right? Because you can view 1 over t as your ft, right? And then when you integrate from constant to x 1 over t dt, this is going to be just 1 over x. Well, that means this is a good formula. You differentiate log x, you get 1 over x. That means if you integrate 1 over x dx, you get back log x plus c. This is new formula and super good, because before when we learn integrate x to the n, right? We say x to the n. If you integrate that, you're gonna get x to the n plus 1 over n plus 1 plus c. But I say that n cannot be negative 1, right? Because if n equal to negative 1, well, just say clearly here. But here, n cannot be -1 because if n equal to -1, your denominator is 0, and that is undefined in mathematics. So this formula, x to the n dx integrate, it does not work when n is equal to -1. When n equal to -1, you're going to use this formula. However, this formula is not completely correct because, well, Peter he's gonna point out what that I am going to say. However, this formula is not completely correct because when we define log x, we define log x to be integrated from 1 to x. That means x must be positive. So that means every time when we say log x, we're gonna put absolute value after logarithm to make it to be defined. So the correct formula is you need to add absolute x. Thank you, Peter. We are going to learn this formula next Monday. But you will see that every time when I integrate 1 over x, we're gonna have logarithm of absolute x. Do not forget to put absolute x. Well, I'm gonna show you ahead of time that next week we're gonna have this formula. This is for next week that we're gonna learn. And once we learn this thing, we can expand the class of function that we can integrate with respect to, because we know how to get 1 over x already. So it's gonna help us a lot. You can see that if you graph the graph of log x, so this is the graph of log x that you need to memorize. So another definition of y equal to log x, you can prove it actually. It's going to be the equivalent form of the inverse of e to the x. So the graph of log x, this is going to be that one. The graph will not touch the y-axis. Even I draw it, it looks like it touch the y-axis. It will not touch y-axis. When you take limit of log x, when x go to plus infinity, this is going forever and forever, just going up, but going up slowly. So limit of log x when x go to infinity, this is going to be plus infinity. And also when you look at limit of log x, when x go to 0 from the left, right, this is going to be negative infinity, because when you approach x, or when you approach 0 from the left, your graph of log x gonna go down, and then it will not touch the y-axis, but it just go down like that. You have no right to say anything about limit of log x when x is negative, when x approach negative number, because that is undefined. Because your domain of log x, this is going to be 0 to plus infinity. Pyridon say that, I think it's correct. Yeah, Pyridon is right. So he mentioned us that the domain of logarithm is positive number. Yes, domain of logarithm is positive number, and that is a good point. That is why every time when we talk about logarithm, we put absolute value, because we do not want the thing after logarithm to be negative. And also the range of the logarithm, this is going to be the possible y values, which is going to be negative infinity, plus infinity, or real number. That is the basic thing for logarithm. Make sense? All right, so we're gonna learn how to differentiate and integrate function that related to logarithm next week, but hopefully I think we're gonna start example 76 next week, but let me show you a little bit about why do we need logarithm. logarithm function. Why do we need natural logarithm? So you look at this. Suppose I have y equal to x squared plus 1 to the 5th power and then square root x squared plus 2x plus 3 over sine 5x plus 1 and then multiply cosec square. No, not cosec is easy. Cosine square tan 2x. What if I ask you to find y prime? How can you do that quick? You want to say, oh my God, Ajahn, I cannot do this because this is ridiculous. How do I differentiate this thing? I have to use product rule and quotient rule, right? Product rule and quotient rule. It's going to be time consuming. It's going to be about half an hour for us to compute this thing by using product rule or quotient rule. But we love logarithm because we're going to have basic property of logarithm. So if you see log of a times b, you can split it into log a plus log b. If you have logarithm of a over b, you can split it into log a minus log b. And also if you have log a to the n power, so you can move n down to n log a. This is a super good property about logarithm because it's going to help us to differentiate as well. Because when you see the function like that, the one that I wrote in red, you can take log first on both sides. So once you take log on the left hand side, so you're going to get log y. Once you take log on the right hand side, you can view this thing as your a. This is your b. This is your c. And this is your d. Different color. This is your a. This is your b. This is your c. This is your d. And then on the right hand side, you're going to have log a times b over c times d. And then when you use the property of log, it's going to be log a plus log b minus log c minus log d and log y here. Is it easier to differentiate? Yes. Because once you have that, you can differentiate with respect to x on both sides. Super easy compared to using the product rule and quotient rule. Because you can differentiate this thing by using implicit differentiation. And then you differentiate both sides and then, well, it's going to be much simpler compared to using product rule and quotient rule. We're going to learn this technique next week that it's going to help us a lot in, reducing work for differentiation. And also it's going to help us a lot when we integrate as well, because we're going to have another formula to integrate 1 over x. And as our good student like Pirasut, Piradon, they mention us that we have to put absolute value of x here, correct? Because otherwise it's not going to be correct. Let's say if I want to integrate 1 over square root x minus 2dx, for example, my answer gonna be log absolute x minus 2. Well, actually I have to simplify it a little bit, but use substitution. But well, when you answer, you have to put absolute. You don't forget your absolute value, because you have to make sure that after logarithm, this is positive thing. All right, we're going to talk about that next week anyway. All right. Any questions before we leave today? All right, Pirasut, good. Piradon, good. Ganpot, good. Sukhvit, good. Okay. Many questions. Thank you, students, for attending today, and especially who participate in the chat. I appreciate it. Anything else? So, well, you can leave something in the chat if you want me. If you want me to have your record. But all right, thank you everyone. So do not forget to download the handout for chapter 4. We're gonna start next Monday, and this is going to be the hardest chapter for midterm. All right. One more thing, homework is due next Friday, so we push it to next Friday. So do not, you don't have to be rushed on homework now. So, all right. Sounds good. Go stay here for questions. If you have anything, I will stay 5 minutes more.
อาจารย์ครับ
Go for it. What is that?
เวลาเปลี่ยนแบบ dx เป็น du เวลา integrate นี่ต้องแบบเช็คขอบของ du ทุกรอบเลยไหมครับแบบเหมือนข้อเมื่อกี้ที่เปลี่ยนจาก1เป็น0นะครับต้องเช็คทุกรอบเลยไหมครับ
I don't know what does it mean by เช็คทุกรอบ
หมายความว่าแบบต้องแบบดูเว้น x เป็นเท่าไหร่ตลอดเลยครับหรือแบบบางข้อมันมีข้อที่แบบไม่ต้องเปลี่ยนจากสลับ1กับ0นะครับ
Well, every time you should do what I just explained. Let's say if you have integrate from integrate fx dx and then you want to integrate x from 2 to 5, for example, and then if you want to pick u equal to be, let's say, x squared plus 1. Okay. Well, when you switch the function to something g of u, right? This is going to be a function of u now. Your du going to be, you have to switch your u to, this thing is going to be, well, every time you have to switch, well, because now you have your x here, and then you switch to u. So once you switch this to u, your lower bound and upper bound that you wrote it here, you're going to write it here, it should represent the lower bound and upper bound in terms of u. Because you keep u to be x squared plus 1, you have to think when x equal to 2, what happened with u. When x equal to 2, you're going to be 5, right? When x equal to 5, you're going to be 26. Well, I mean, from this formula. So that means you have to say this is 5 to 26. Sounds good? Is that your question?
Thank you, teacher. I understand what you say.
Does it make sense?
Yes.
I cannot remember who asked me. Does that answer your question?
Yes.
Yeah.
Thank you, teacher.
Yeah. All right. Anything else? All right. If you don't have anything else, so keep in touch via line or something, email, whatever. So let me know if you have any questions. So that's the end of the lecture today. Thank you, everyone.